Hello everyone, welcome to the new video. So in this video we are going to learn about the finite automata model, the definition, and also how can we represent the finite automata model. So let's get into the video. So a finite automata model has three main components. The first one is an input tape, and the second one being read head. The third one is finite control. So let's draw the diagram for it. First one is an input tape. So input tape consists of so many number of cells where each cell is composed to contain one symbol. So for now we'll take our symbols as zeros and ones, and this is our input tape. The second component what we have is our read head. This is our read head, and the read head first points to the first element or symbol of the input tape, and it goes from right to left covering the next element, the next element, the next element, and the last element. And this read head is connected to a machine which is our finite control. And in this finite control it stores all the states information, and what happens if the state points to the particular symbol. For example, our state right now might be q naught. So if this is our first element what we encountered here, so if the current state is q naught is encountered with 0, it has to go to the next state. All these kinds of information will be stored in this finite control. I guess you understood how to draw the diagram. So now let's see how can we define finite control. So finite control is defined with five major elements, where M is our model and it has Q, sigma, transition function delta, Q naught, and F. Here Q is the set of all states, and sigma is a set of all input alphabets what I am using here. Set of all input alphabets, and this is a transition function. And transition function helps to which state we have to go when we encounter a particular alphabet. And q naught is our initial state, and we do have only one initial state in any finite automata. And f is a set of all final states. And if you can observe here, we have only one initial state, and we can have more than one initial states, sorry, more than one final states. This is how we define finite automata. So let's see how to represent finite automata. So finite automata can be represented using either transition diagrams or using a transition table. Here diagrams means it is a kind of a pictorial representation of finite automata, and table is a tabular representation of the finite automata. And in any finite automata we find two states which are compulsory. The first one is initial state, and the second one is final state. by states also, because we might have more than one states. So initial state is represented with an arrow pointing inward towards it and the name mentioned inside the circle, and the final state is represented with a dual circle and the name inside it. For example, let us take an example of a diagram of q naught being our initial state and q1 being our final state, and when applied with a it goes on to q1, and when applied b it stays on itself, and q1 when applied a goes on to q naught, and when applied b stays on itself. So as we have already discussed of how to write a formal definition of formal automata, let us write a formal definition for this diagram. So any formal automata is defined using 5 tuples, being q, sigma, delta, q naught, and f. Here q is a set of all states. So what all states we got here? Q naught and q1. So q is q naught comma q1, and sigma. Sigma is a set of all alphabets. So what are alphabets did we use here? A and B, A and B. So A and B. And transition function delta we'll talk about in a minute. And q naught is our initial state. What is our initial state here? Q naught is the initial state. So our initial state is q naught. And f is a set of all final states. So we got only one final state here, which is q1. So our final state here is q1. And coming to the transition functions delta, delta of q1 q naught when applied with a goes to q1, that is when the state q naught when applied with a the state changes from q naught to q1. So q naught when applied by a the state changes to q1, and delta of q naught comma b, and when q naught is applied with b the state changes to q naught, that is it remains same, it is equals to q naught, and delta of q1 comma a, when q1 is applied with a the state changes to q naught, q1 applied with a state changes to q naught, and delta of q1 comma b, and q1 is applied with b the state remains same, that is when q1 is applied with b the state remains same and it is q1. So this is how we represent the formal definition using the diagram. Let me draw the table, it's here itself. So what all states do we have here? We have one initial state being q naught and one final state being q1. This is how we represent it with an arrow and this is a circle. And what all input alphabets do we have? A and a B. So using this transition functions, we'll write down this table. Q naught when applied with A. That is Q naught when applied with A goes to Q1. So Q naught when applied with A goes to Q1, and Q naught when applied with B. And Q naught when applied with B remains on Q naught. So Q1 on B remains on Q1. Q1 on A. So Q1 on A goes to Q naught. This Q1 on A goes to Q naught, and Q1 on B. Q1 on B state changes to Q1. That is, sorry, the state remains same. So Q1 on B the state remains same. That is Q1. So this is how we represent a formal automata using a table. This is called as transition table and it is called as a transition diagram. I hope you understood it. So thank you guys.